Hi, this is Mrs. Villette, and we're continuing with section 6.6. We are solving equations with logarithms, and we'll continue after these videos onto a worksheet and do a few more examples with exponentials and some other equations. So I want you to remember that last week we were working on properties of logarithms, and this is where these properties of logarithms are going to come up again. So we are going to solve log base 2 of x, subtract log base 2 of x plus 1 equals -1, and we're going to check numerically and graph. And we've done some equations with logarithms and exponentials, but never an equation that had two logarithms. So what we want to do is we want to try to get rid of the fact that there are two logarithms. Ultimately, we want to get rid of the logarithms completely. But the first thing we want to do is actually collapse these logarithms down into a single logarithm. And we do have a rule from section 6.5 that lets us do that. We can turn this into the log base 2. Whenever I had the logarithms subtracted, I could divide their arguments. So equals -1. Now, one way we can get rid of the logarithm is just translate. Another way that we can do this, which I don't think you've seen yet, is we can exponentiate. And what we're going to do is we're going to make this whole entire equation the exponent of an exponential with a base of 2. So what I really have here, I'll just rewrite it so you can see, I have 2 to the power log base 2 of x over x plus 1 equals 2 to the -1. Our cancellation properties say that when we compose an exponential function with a logarithm of the same base, they cancel each other. And so I'm left with x over x plus 1 equals 1 over 2, because 2 to the -1 is the same thing as 1/2. Now, since this is a rational equation, I'm going to clear the fractions by multiplying both sides by the lowest common denominator, which is 2 times x plus 1. And on the left, the x plus 1 cancels, and on the right, the 2 cancels. And so I have 2x equals x plus 1. And if I subtract x from both sides, I just get x equals 1. Now this says check numerically and graphically. The reason that we check in these equations is there is a chance that we could get some extraneous solutions. So possibly we could get a value of x when we did this log property and combined them that worked here in the ratio, but actually is outside of the domain of either of these functions. Now I can already tell that it's not going to happen. Our domain, so this is something that maybe you want to get in the habit of doing before you start the problem. Our solution domain for the first one is that x has to be greater than 0, because the input to a logarithm, similar to a square root, has to be positive. For a square root, it could be greater than or equal to 0. For a logarithm, it has to be greater than 0. So for the first one, the x has to be greater than 0. For the second one, x plus 1 has to be greater than 0, which means x has to be greater than -1. If you put those both on a number line, here's -1, here's 0, we're looking for the overlap. So here are my two possible solution domains, and the overlap would be this part, that x has to be greater than 0. And the value of x that we got is 1, so that is greater than 0, so we know it is in the solution domain. So now when we're checking, we're not really checking for extraneous solutions, we are just checking to make sure that the solution we found is actually the correct solution. So I'm going to put x equals 1 into my equation, and when I do my check, I want to avoid doing anything I did in the solving step. So I am not going to combine these logarithms into a single logarithm. I am simply going to evaluate each one on its own. Hopefully you have recognized by now that all logarithms have an x-intercept at 1. So this value is 0 because basically we're thinking 2 to the what equals 1. The answer is 0. So this is 0. So now I have 0, subtract log base 2 of 2. Does that equal -1? Well, 2 is 2 to the 1. A logarithm is saying what's the exponent, so log base 2 of 2 to the 1 is just 1, so I get -1 equals -1, which checks. So we'd go back over here and our final solution set would just be 1. So now let's go ahead and take a look at another logarithm problem that has 2 logs, but I don't need to use one of those properties. What we're going to use here, and this only works when all you have is 2 logs of the same base, one on either side and no extra constant terms. What I'm going to do here is similar to what I did in the last problem. I am going to exponentiate. So I'm just copying the problem down. I'm going to go ahead and erase the equal sign. I'll put it back in a minute. Since these are both log base 3, I am going to make both of them the exponent of an exponential with the same base, and then we just use the cancellation property. So cancellation, cancellation, and we have x squared plus 1, don't know why I changed colors, but we'll go with it, equals -2x. Now this is quadratic, so we'll go ahead and move everything to one side. X squared plus 2x plus 1 equals 0. And then if we factor, hopefully you recognize that that is the square of x plus 1, so we get x equals -1. Now we'll go ahead and check. And on our check, we are plugging in -1 to both sides, so log base 3 of -1 squared plus 1 equals log base 3 of -2 times -1. Log base 3 of 2 equals log base 3 of 2. Well, obviously, the thing that we want to remember about logarithms is they are one-to-one functions. So we could have kind of shortcutted things here and just said, hey, these are both the same function on the outside. Let's just get rid of it because they're one-to-one functions. We know if the outputs are the same, the inputs are the same, and then we would have just solved this same quadratic equation here. Now this, we did check numerically. We did not check either of these equations graphically. So let's see what that looks like. So I've got Desmos here, and I've already entered the first function. So I've entered y equals log base 3 of x squared plus 1. When we're solving graphically, we graph the left-hand side, we graph the right-hand side. Now, you are not expected to know that the graph looks like that. Now I'm going to enter y equals, I go to functions, miscellaneous, log base 3 of -2x. And we can see that there is one place where they intersect, and the x-coordinate of that intersection is -1. Now going back to example 4, we're also going to solve this one by graphing. We already did the numeric check. One thing that I've noticed in Desmos is a lot of people tend to leave the y equals out, and that's fine for functions that have x's in them. But if I just put in -1, Desmos doesn't do anything with that. So it's really important when your other side is just a constant that you put the y equals. So I'm going to put in y equals -1. Again, when we're solving by graphing, we're graphing the left-hand side, y equals, graphing the right-hand side, y equals, and then we are looking for their intersection, and we're looking for, in particular, the x-coordinate of the intersection. And 1 is the solution that we got on this previous problem. So that is it for what goes along with the notes, but you will see a section 6.6 practice worksheet, and in the next 1 or 2 videos, I will go through some examples on those, and the rest will be left for you, but there is an answer key so you can check your answers.